Welcome to my podcast, Jack to the Future. From science and inventions to pollution and recycling, I talk about what's changing in the world, the future, and how we can help with that. Every month I'll talk about a different future theme. For example, the future of science, tech, sustainability, reading, music, and all sorts of other ones. The future of everything. Did you know? You can find me on Facebook and Instagram as Jed to the Future and on YouTube as Jack to the Future. Follow me to get behind the scenes info, access to the previews about my next episodes, and much, much more. This week's episode is about the future of deep space communications. I interview Ed Chester, who is a systems engineer and works at the Goonhilly Satellite Earth Station. If you follow me on social media, you may have seen in my episode teaser a picture of Ed with a giant question mark behind him. That was of course covering up a giant satellite. Two of these satellites at Goonhilly use radio waves to send and receive signals that support spacecraft missions which start at a distance of 2 million kilometres from Earth. We talk about how the satellites work, what deep space communication might look like in the future, whether we could live on any other planets, and what meeting one of my heroes, Tim Peake, was like. So, the future of deep space communication. To be honest, I didn't really have a clue about this topic before we recorded this episode. There's a really good NASA video for children on YouTube, which I'll ask my mum to put the link into the description. Basically, spacecraft send images and other information to these big antennas. The antennas also receive details about where the spacecraft are and how they're doing. At the same time, the space agency are responsible for the spacecraft, like NASA, for example, can use the antennas to send lists of instructions out to the spacecraft. In terms of the future, what I did notice is that the antennas are massive, and we don't have a lot of space on Earth. So maybe the future of communications systems to space is that there could be another structure to transmit radio waves that's smaller, or maybe a structure that communicate with more spacecraft at once and quicker. Have you got any ideas? I'd like to welcome my special guest today, Ed Chester, who is a deep space systems engineer and works at Goonhilly Satellite Earth Station. He is also a volunteer STEM ambassador for the IET. Thanks for being here today.
Hi there.
Hello.
Very welcome. I'm very excited to have the opportunity to talk to you. I'm very impressed with your podcast series.
Thank you.
So what's your favourite thing about the film Back to the Future? Why do you like that so much?
Time travel.
Time travel. I'm still waiting for hoverboards to be invented.
Oh my, I really hope they will be invented soon. Because in the film it says it's like in 2015 they thought that hoverboards would be invented.
I know. They're late, aren't they?
Yeah.
I think if you could gather all of the engineers and all of the physicists in one place and you ask them about time travel, I think firstly they wouldn't agree, but also I think the huge majority of them would probably say it can't be done. So
well, for now.
Yeah.
I think going backwards in science is always easier. Past has already happened.
I think don't hold your breath is the message on time travel. Or accept that you're time travelling forwards all the time.
Yeah, you are. You're a deep space engineer. What does that mean?
Okay, there are two parts to that name, deep space and systems engineers. I'll talk about systems engineer first, because one of the really fun things about being a systems engineer, even in the industry, is that actually people don't usually know what it means. And that's a good thing, but also sometimes that's a bad thing. So you don't always have people understanding what your role is. To understand what a systems engineer is, we need to really look at what a system is. And by a system, we mean the entire machine, set of machines or parts that go into solving a problem or performing a function or anything else. So if we're talking about a space mission, then the spacecraft is part of a system, but so is all the equipment on the ground that communicates to it. And so are the people who plan what it has to do and work out the schedule, and the scientists who deal with the data afterwards. All of those things are parts of a system. And the job of a systems engineer is to understand how the whole set of stuff works together. In particular, if we make a simple example, we have a spacecraft that has maybe a camera on it, and it has batteries, and it has a radio, and it has solar panels to get power into the batteries, and it has a computer to store data and process information and to also hold the schedule. All of those different things are made by different experts, and they have engineers that specifically look after those parts. So you might have a power engineer, you might have a mechanical engineer who's looking at the structure, you might have a radio engineer looking at the communications. But the job of a systems engineer is not to understand how all of those blocks work in detail, but is to understand how do they work together to make a machine that works? And the real job of system engineers, what we call the interfaces. So the parts of a unit, for example, a battery, the interfaces to that battery are where it has to connect to every other part of the machine. So a battery would have interfaces that are electrical, they deliver power, but it also needs to have mechanical interfaces. It has to be held in a structure. It also might have a little bit of an abstract thing, a thermal interface, because heat flows in and out of batteries as well. And so all of those things are how that element interacts in its own environment. And the systems engineer's job is to understand all of those interfaces and to make sure that when they're all put together to make one machine, one mission, one system, that it is all going to work the way it's supposed to, without having necessarily to understand the fine details about every part. Deep space just means that I do that sort of work for space missions that are going to deep space. So what do we mean by deep space? Well, space is organized in a little bit of an arbitrary way into near Earth missions and deep space. Now, near Earth really is just a way of saying if you're close enough to Earth, then the gravity of Earth is really important for your mission. You're affected by the Earth and the Moon, the system of the Earth and the Moon together. And that dominates what you experience, where you're going to fly, the characteristics of your mission. If you're further away, then the gravity of the Earth, the effect of the Earth is less and less important. Now, that distance is agreed by convention to be 2 million kilometers. Now, that's not to say that at 2 million kilometers, all of a sudden, the gravity of the Earth switches off and you can forget about it, but it gradually fades out.
Wow, yeah, that's a really good explanation for it. Thank you. I really want to be a systems engineer, especially a deep space one. That sounds really cool because systems engineers is like the mechanical parts of a machine. I really like to design and kind of do the things that you do. I like to have that as a job.
There's not usually many systems engineers in a team. Now, that means that a lot of the work of a systems engineer, unfortunately, is just sitting with computers and writing documents and reading documents. But it's also fun to have the sort of responsibility for making sure that everything works together. So I think it's a really fun thing to do. Some people like doing that sort of work. It just depends on how you approach problems, I think.
Yeah, there's downsides and upsides of being a systems engineer. Even if there is a downsides of it, I still probably wouldn't mind reading documents, to be honest. I mean, I quite like reading things about making systems for machines. I think I'd probably quite like that.
Yeah, I think it's really rewarding.
Yeah. I recently did an episode on the future of radio and I learned about transmitters and receivers. Is that how the deep space antennas work too?
Absolutely. It's just like having walkie-talkies, one just very, very far away and one here on the ground. I've got to be a little bit careful, but I'm going to start by saying all communication so far between spacecraft to the ground has really been just using radios. And there is an alternative to that, which has been used in space, really just to demonstrate it's possible, which is to use lasers to basically shine laser light between spacecraft. A lot of possible advantages, but we don't use that to talk to them from the ground yet.
I think those lasers would be a good idea. It could be like a beacon holding information, and then you could get some sort of mirror or something that would bounce it, and then it could go into different ones and they could collect the information.
Exactly.
Yeah.
That is a really good idea. Really big problem with using lasers instead of radios. And that is that lasers really just travel in one direction. So you really have to point exactly where you want to shine your laser to get the information to travel to where it needs to be.
It has to be exactly in the right position.
Exactly. And that's quite difficult, actually, particularly the further away you go, you have to be even more accurately pointed because it's about even very small angle pointing the wrong way. By the time you're 1 million kilometers away, that you could miss the planet altogether. So lasers are very promising because you can put huge amounts of information over a laser link very, very quickly. And that's a lot how the internet works on the ground, is fiber optics with lasers inside. So you can put information through them very, very quickly. But it's very, very difficult in space to get them to line up in a reliable way every time.
Yeah.
And that's the advantage of radios. Radio waves are quite wide.
Yeah, because on the Earth, when you shoot the laser, in space, it will be not in the same line. It will be a different position. So you have to move it right where it is. Because if you lined it up perfectly from the Earth, let's say you had a huge ruler and then you turn the laser on, it would completely miss it because it's in a different position.
Because it's so far, it takes time for even light to go from where it's being transmitted to where it's being received. So if you shot it straight out to where you wanted it to be received, you actually need to point it to where the spacecraft is going to be instead of where it is now. So that is quite difficult to wrap your head around, actually.
Yeah, so like estimate which direction, how fast it's going. Yeah, that sounds hard. So at the moment, radio is better. It's like radio waves or wiggly.
Radio spreads out, so you can cover quite a big area.
Yeah, how can the signal actually travel that far?
It's quite staggering to think about how far we can send radio waves. But the only thing that stops them really is our atmosphere. So once you've got a radio that can transmit through the atmosphere, those radio waves are just going to keep going. Now, they do get weaker and weaker and weaker all the time. And what we have to do is choose frequencies or parts of what's called the electromagnetic spectrum that atmosphere doesn't really block it very much. Okay, so there are some parts of the radio spectrum where it's quite hard to transmit through the air, basically because of water. All the moisture that's in the air absorbs that energy. But if we avoid those frequencies, we can send radio waves out into space and then they just keep on going. So the fact that they can travel so far isn't really by itself a surprise. What is quite amazing, I think, is that even when those signals have gone hundreds of millions of kilometers and they're so weak, because they're spreading out all the time, the further away they go, we can capture them with an antenna and then amplify them and boost them back up and then understand those signals. We can decode them and get information out of them. And that's what I find staggering, is that the amount of actual energy that makes it all the way through space and then lands on an antenna, that amount of energy is phenomenally small. And yet we can somehow capture it and turn it back into useful information.
Uh-huh. Yeah.
So you're absolutely right. It's very strange that we can communicate so far. But the fact is the radio waves are going to keep going forever. And the radio waves that were set off as soon as radio was invented have now, left the solar system. And those radio waves are still traveling. They're just incredibly weak. So our technology that allows us to listen to very weak signals, that is quite staggering, really, rather than the radio waves themselves.
Yeah, so it's amazing.
Mm.
Yeah. You have 2 deep space antennas at Goonhilly. Does that mean you can only communicate with 2 spacecrafts at a time?
Right, we can communicate with 2, in inverted commas, deep space spacecraft at the same time, but actually anything that is in essentially the field of view, so anything that's in the direction that the dish is pointing, we could communicate with. So one of the things that we did very early on when we made this station was pointed at Mars, which is a very busy place for spacecraft at the minute. We saw 4 different spacecraft in the signal all at the same time.
Mm.
So we can't communicate to the spacecraft. We can't transmit at the same time to all 4 spacecraft.
No?
But in principle, we could listen to all 4 spacecraft. We could receive from anything that is pointing in that direction.
Ah, okay.
So one of the interesting questions is, can we use this system to transmit as well? And there are ways of doing it, but it's a little bit complicated and takes a lot of coordination.
Okay, yeah, that makes sense.
So we do have 2 dishes of about this size, this one and another one, and they independently can communicate with different spacecraft. The only reason that we call them deep space is that they're big enough to be able to amplify really, really weak signals enough that we can be listening to spacecraft that are more than 2 million kilometers away and even further. But around the site, and you can see here poking through the trees, there's another antenna there, and there's dozens of other antennas as well. We have antennas that belong to us on site, and we also have antennas that belong to our customers, and they like the site and they use, for example, our internet connections and our power systems because they're very reliable and high capacity, and they communicate from the same site. So actually there's lots and lots of spacecraft get communicated with all the time from the same place.
Yeah.
It's quite a scary number. And every time I go, I see more.
Yeah, it's not on my list of questions,
Okay.
But when we were researching for this podcast, we were looking at just how huge the antennas are, and I wondered in the future if you think the antennas might become smaller because they use up a lot of space on the ground.
That's a really good question. So there's only a couple of factors that affect the performance of an antenna. And for something like deep space or tracking a spacecraft that's a long way away, the most important thing is really just the size, the physical size of the reflector that is gathering signal. So the more signal you can gather, the better chance you have of being able to use that signal and then decode it and so on. So the only reason this is as big as it is because the signals from very, very far away are very, very, very weak. And the more of that you gather, the better that link can be. But the disadvantage of it being so big is that it's then very difficult to move it quickly. So there's a building underneath that I'm pointing to right now. Everything on top of that building is on tracks and moves this way and it tips. And the whole of that weighs about 400 tons.
Wow.
And we have to point it very, very accurately, which means you can't do that quickly.
No.
So we are limited in being able to communicate with a big antenna to spacecraft that don't move across the sky too quickly. So some satellites that are very, very close to Earth, for example, fly across the sky really fast. They come up on one side and then maybe only 6 minutes later, they've set on the other side of the sky. So you have to move really, really quickly to track them. And we can't do that with an antenna this big just because it's so heavy. So we have smaller antennas that can move really quickly for tracking satellites that are nearer. We have these two really big ones for deep space. We have some that are roughly half this size, so sort of around 15, 16, 17 meters. Then there are several much smaller again, sort of 10 to 12 meters across. A whole group that are only about 5 meters across. A couple that are maybe 2 meters across.
How big would that be? A whole like dish that big?
The whole thing.
Oh.
So the thing is, that doesn't weigh very much. You can point it extremely quickly, which is really good for satellites that are very close to the Earth.
Yeah, because the smaller it is, the easier it is to communicate that.
Right.
Yeah. Did you get to meet Tim Peake when he opened the upgraded antenna at Goonhilly? I'd love to meet him.
I didn't meet him when he opened this antenna, no, but I have met him a couple of times.
What's he like?
He's very, very friendly, very kind person, clearly very passionate about communicating the role of space. Why do we explore space? Why do we put satellites into orbit? And it's not about spending a lot of money and doing things that are very exciting. It's because it's genuinely useful. So he's become a really strong advocate for that.
Yeah, I really want to meet him. He's like probably one of my favourite celebrity. Your antennas are helping with the Mars Express mission. Did anyone go inside the Mars Express, or is it too hot on Mars?
Nobody goes inside. It's not a human mission. There have been no human missions to Mars yet. Mars Express is a robotic probe mission. It flies by itself. It's like a satellite. But when we use the word satellite, we really mean things that are going to orbit around the Earth. So Mars Express isn't in orbit around the Earth. It's now in orbit around Mars, and it's been there for years doing science, and it's designed to carry different instruments, different scientific experiments to understand and explore the environment and the processes that have shaped Mars the way it is today. And it can do that really well without people being on board. But it's not close to big enough to put people inside. I mean, you could squeeze a person in, but then there wouldn't be room for anything else. It's like a cube.
How big is it?
2 meters to the side, so it's not that huge. But the real reason about people not going in there is not because it's too hot on Mars, because it really isn't too hot on Mars. In the middle of summer, at the equator on Mars, it's a pretty comfortable kind of 20 degrees. It's a lot like it is here. At night, it gets a lot colder. And if you get away from the equator and you get up to the polar regions, obviously it gets a bit colder as well, like here.
I thought it was really hot because it's called the Red Planet. Would people be able to live on Mars? Would it be the right sort of weather?
The real problem with Mars is that it does have an atmosphere, but it's completely the wrong kind of an atmosphere to keep people alive. There's essentially no oxygen as we need in our atmosphere here. And it's also at very, very, very low pressure. So there's not nearly enough gas at the surface for us to breathe, to survive, even if it was made of oxygen, the things that we need. So it's nearly all made of carbon dioxide, and it's got a bit of other stuff in it as well. But it's very, very, very thin. And part of the reason it's very, very thin is that Mars is just so much smaller than Earth that it has less gravity. So that kind of means that the atmosphere isn't held on and doesn't have the same pressure at the surface that we have here on Earth. So could people live on Mars? They could, but they couldn't live open on the surface. You would have to live inside an enclosed space, like maybe a dome or some other structure that had inside it an atmosphere that had been created using machines at the right pressure with the right gases in it. Now, that's quite a difficult thing to set up. So
yeah, if you just kind of made a dome.
I don't know that would ever happen, actually.
When I was doing research for this podcast, I read that the Mars Express had made an amazing discovery of a water source on the planet. It was a whole lake. It was a lake.
Yeah. So one of the instruments on Mars Express is a radar that allows us to see under the surface. And there's a huge amount of ice under the surface of Mars. And in parts, we even think there's liquid water because it's sufficiently warm that it's not frozen into ice, but under the surface, potentially quite a long way under the surface. But Mars absolutely used to be a warm, wet planet. I mean, if you imagine our moon today, something that sort of size, if you imagine taking a colossal jug of water and just pouring water into it, you would end up with something that would be quite like Mars billions of years ago. That's why it's an exciting place to imagine finding very simple life forms. So bacteria or things like that might have started there.
A long time ago on Mars, would there probably have been like oxygen on it? Or
I don't think I know enough about the atmospheric chemistry of Mars to know for sure, but there definitely was much more atmosphere than there is today. And we know that there are oceans on the surface and seas and lakes and rivers. And so the whole presence of flowing water pretty much requires you to have an atmosphere. And we can see the evidence for all of that in the physical features that have been left on the surface. So there are river valleys, the edges of ancient seas, erosion features where water has been flowing, and the particular deposits to minerals, things that used to be made in a wet environment, have been left behind on the surface. And that's one of the key science questions from the recent missions to Mars, has been to look at what are these minerals and how long have they been there, and are they the result of natural geological processes, or are they potentially, in some cases, the result of biological processes, so meaning some form of life. It's all tied into the really, really big question of, are we alone? Has life ever begun somewhere else? And I think probably 30 years ago, we were really kind of unsure about that. And I think now if you talk to anybody involved in planetary sciences, in particular Mars exploration, they would be quite comfortable with the idea that actually not only was there some basic form of life on Mars, but actually that life is everywhere in the universe. Obviously, not every planet is going to have it, but there is such a wide range of things that life does on Earth to survive. We find microbes in the worst imaginable conditions with no light, no oxygen, extreme heat, extremely acid environments on Earth, and life is just getting on with it. And we also find it in the exact opposite of those conditions. So the idea that somehow we couldn't have microbes in another place is really unlikely.
Yeah, I think probably not really human life or like alien life. I think it'd probably be like something to do with microbes that we haven't discovered yet, which live on other things. And
Absolutely.
also on the moon, that big cube, I think aliens made it. I think they probably did. You know what I mean?
I've not heard about this, no.
They'd seen a shadow on the dark side of the moon that looked like a cube, but I haven't heard any more about that actually, so maybe it was fake news. I'll have to look it up.
Sometimes nature does things that look really artificial, and you have to be a little bit suspicious of it.
It didn't make a lot of sense, to be honest, because there was so much monitoring going on. How would that have suddenly appeared anyway?
Have you ever heard of the Giant's Causeway?
Yes, I've been.
The rocks there are made of beautifully regular hexagons with dead straight edges.
Oh, yeah.
It looks like you couldn't make those yourself if you had a machine and a ruler and everything else. So sometimes nature does amazingly regular things that look like somebody must have made it, but actually it's a completely natural process.
Yeah. I'm going to ask you something, which probably isn't true, but I think they're saying that Neil Armstrong, if you go in for Neil Armstrong, spell Neil A backwards, it spells alien. And he went to the moon, so I thought it might be an alien. You don't know. I think it's probably just a coincidence, his name.
I think it
Yeah.
is. Yeah.
I just thought of that.
Have you heard of a place called Europa?
Yeah.
You have?
Yes, I have.
Do you know where it is?
Not exactly.
So it's an ice moon.
Jupiter, isn't it?
Yeah. But one of the things we know about it is that if you go down beneath the ice, there's a whole ocean. It's like a moon that's covered in a very, very deep ocean that's then got a layer of the ice on the outer surface because it's very, very cold. And a lot of people are pretty excited about what might be happening in that ocean. It's liquid water, so it's flowing around. So it has source of heat, water. It's going to be rich in minerals, other conditions that created life. There's a number of different missions that have been proposed to explore Europa, one in particular called Europa Clipper that I think is still in development.
That's interesting.
But that is, I think, everybody's favourite possible place in the solar system to look for little like microbes, as you say, or I like to imagine even kind of fish and things swimming around in that ocean.
Or maybe some sort of like aliens having it as their swimming pool for their swimming lessons. Who knows?
Who knows?
How do you think people like you might help with more deep space discoveries in the future?
Well, I think the important thing is it's a whole team of people. But the key thing about exploration, not just space exploration, but on the Earth and in the oceans and everywhere, is that really it's finding out what are the questions that you want to answer and agreeing on those questions as a science community. What are the priorities that is possibly within our technical ability to make a machine or a system to address that question? Pushing the boundary of science is about imagining questions that are built on the knowledge that we've gained so far. And once there's a scientific way of trying to answer that question, then engineers get involved in terms of how do you make that experiment or that instrument in a way that you can put it into the environment it has to work in. So maybe if you're exploring the oceans, you're talking about making a version that uses low power and is miniaturized and is waterproof, and you could put it in a little submarine or whatever it is you need to do. Well, if we're talking about space, can you make it in a way that it can go on top of a rocket? It will survive launch and it will survive being in potentially extremes of cold. There's a lot of people involved in planning and the modeling and scheduling, all the aspects of how you put a mission together. It involves politics, it involves lawyers, it involves business people to fund. And I really enjoy being an engineer, and I really hope to continue to be involved in missions. Some of the future missions that we will support from Goonhilly are going to the moon. It's been a long time since the moon was really a high priority, but it's so close and so accessible now that really a lot of different ideas are cropping up for how we can begin to make use of that. Maybe not to go and live on, but as a place to, for example, generate power and beam it back to Earth, as a place to use to relay communications without having so many satellites, as a place to do science and to understand the formation of the solar system, because the moon is really a living fossil of the material that existed at that time. It hasn't had water flowing around on it. It hasn't had an atmosphere to speak of. So the surface of the moon really is in the same condition it was in when the solar system was formed. And it's very exciting to have that just really on our doorstep. It's only 250,000 miles away.
Oh, yeah. I think it'd be good if we could use the moon to help with some of our planet's problems. What do you think the future of space communications will be?
Okay. I mean, we talked a little bit about lasers, but I think really we will be using radios the way we use them today for a very, very long time. But we could use them in a much more organized way. Right now, we talk from the ground to a spacecraft, one spacecraft to one ground station, and we could be much more imaginative about how that works. So we are looking now at, for example, putting relay stations around the moon and around Mars so that future missions to the moon or to Mars, instead of having to communicate all the way back to Earth, can just communicate to a local relay that then at another time does the communication to Earth. So it's a little bit like setting up a whole network in each location that we want to explore. So we put a network around the moon, a network around Mars, and then even connect those two things together, possibly with lasers when we're not worried about the atmosphere. And essentially, the technology that allows us to do that is internet. We want to put the internet out to the moon and out to Mars orbit as well. So then if you put a machine there, it's much, much easier to communicate with it. So that's coming.
This is really cool, yeah. So let's say if you were able to live on there, you'd be able to finally go on your phone.
Yep.
It'd be quicker. Because sometimes the internet lags. And
so reliability is a really big issue, because if you just have one link and then there's any problems on that link, you've lost that link. But if we set up something a little bit like an internet type architecture at the moon or at Mars, then there's more than one route for information to flow. So if one route doesn't work for whatever reason, then the information automatically will be routed via a different route. So the reliability will go up, the amount of information we can send will go up, but the difficulty of doing it will come down because you don't have to transmit for so far.
Yeah, it's really interesting.
Good idea.
It is a good idea, definitely. Thank you for joining me today, Ed. I really enjoyed it, and probably my favourite bit was when we were talking about when you got to see Tim Peake, because that was really exciting.
Well, it's been really fun to talk to you, Jack. Often, I think, in professional lives, no matter what you do, you often get too close to what you do on a day-to-day basis, and taking time to discuss it with other people who are interested is very rewarding, and it kind of reminds me about why I love what I get to do. it. So it's been really good fun. Thank you.
You're welcome. Bye.
Bye-bye.
That's all we've got time for today. This week's episode has gone way beyond deep space communications, but it's been so interesting. Lasers, time travels, ice moons, natural phenomenon, and alien life forms, to name but a few. My mum will put a link in the podcast description to an article about Europa, as well as the Goonhilly Earth Station website, and anything else she can think of that we talked about. And as for the tube-shaped rock on the moon that I talked about, turns out it was actually just a rabbit-shaped rock. So all that hype, and it's a rock that's not even shaped like a cube. Anyway, my mum will put a photo of it on social media and a link to the press article in the description. Although Ed seemed to think time travel was a distant dream, I'll settle for the idea that we may be able to have internet in space soon. Talk about E.T. phone home. Join me next time for another exciting episode of Jack to the Future.